In this video, we're going to look at analyzing graphs of functions, and we're going to take a look at piecewise functions. So far, we've defined what a function is, and we've transformed graphs of functions based on whether things have been added or subtracted, or negated, or multiplied by a scalar. And so we've looked at those transformations, and we've defined what a function actually is. But in this one, we're going to actually or analyze the graphs of functions and piecewise defined functions. So let's get started. Here we go. So first thing we want to think about when we're analyzing graphs is we want to think about the symmetry of the graph. Symmetry is kind of like, you can think of it as mirror images. So you might have learned about symmetry in shapes, like a heart. If you fold it down the center of a heart, it would fold over onto itself and it would be considered symmetric. And so we're looking at the symmetry of these different graphs. We talk about symmetry with respect to specific lines or points. So if we say a graph is symmetric with respect to the y-axis, that means it could reflect over the y-axis and it does not change the graph at all. So it'd be like folding a heart over and then pulling the other side back to the right. So I'm like moving my hands, which you can't see, but it'd be like if you flipped the heart over around that middle line, it would still be the same heart. It wouldn't change at all. And so that's like reflection over the y-axis. Symmetric with respect to the x-axis is a reflection over the x-axis that has no effect on the graph. So if you flip something up and down through a line of symmetry, and in this case it would be the x-axis, and it didn't change the shape at all, then we would say that it's symmetric over the x-axis. And then symmetric with respect to the origin is when something gets reflected over both the x-axis and then the y-axis, and it won't change the graph. Okay, this would be the same thing as a 180-degree rotation. Let's look at a couple of graphs and determine what kind of symmetry the graphs have, whether it's with respect to the x-axis, y-axis, origin, or none of the above. So this first one in blue, you can see that if I were to flip it over or reflect it over the y-axis, this point would flip over to here and vice versa. And that's a true statement for every, well, draw my points right, for every point on this graph. And so therefore, this graph has symmetry with respect to the y-axis. This graph in red, if I were to reflect it over the y-axis, it would not match up. But then if I were to then again reflect it over the x-axis, it would end up matching up. So it has that symmetry where if you reflect it over both the x and then the y, it will not change the original graph. And so therefore we say that this has symmetry around the origin, or with respect to the origin. Because again, if I were to reflect over the y and then reflect that point over to the x, it goes to the original point, it goes to an original point on the graph for every point on this function. The reason why this idea of symmetry is important is because it helps us identify even and odd functions. So an even function has y-axis symmetry, and odd functions have origin symmetry. So if you were trying to determine its symmetry or its evenness or oddness based on its graph, you can look at its symmetry and make that determination. Let me draw a quick sketch of a graph that does not have any of these symmetries. If I had a graph of a function that was like this, okay? I don't know why I made that sound effect. There's no way that I could reflect this over the x, the y, or the origin, or about the origin to get the same function that I had originally. And so this does not have any symmetry. All right, let's look at some even and odd functions and the definition of an even and odd function. The way we can determine from an equation if a function is even or odd is by finding and simplifying f of negative x. Okay, if you do f of a negative x and you get the same result as what f of x is, then it is an even function. So for example, if I say my f of x is x squared, f of negative x would be equal to negative x in parentheses. And when you square a negative number, you get a positive number. So this is the same thing as saying x squared. So therefore, the function f of x equals x squared is an example of an even function. If you were to graph that function, we know it looks like this. We would say it has y-axis symmetry because if I reflected over the y-axis, each point would match up to a previous point on the function, and it would not change that graph at all. So even functions have that y-axis symmetry, and we can see an example of that with the x squared quadratic parent function. So now we're going to look at odd functions. When you find and simplify f of negative x, if your result has the opposite sign of the original function, then it is odd. So I'm going to do an example in red where you can see where that happens. Note that odd functions have origin symmetry. So that's where it's reflected over the x and y, and we'll give you the original graph. So our most common, I would say, odd function would be f of x equals x to the third, because when I find and simplify f of negative x, I end up getting negative x to the third, but negative x times negative x times negative x equals negative x to the third, like negative x to the third. So we've negated the original function, and so therefore this is an example of an odd function. So we ended up with f of negative x actually equals negative f of x. That's our common kind of rule of thumb. If I evaluate the negative x value and I get the negation of the original function, then it's odd. Versus for the evens, when I did f of negative x, you actually just get the original f of x. Okay, so the difference between even and odd. Okay, so then we can use this fact to determine whether or not our functions are even, odd, or neither. So let's do that. We're going to find for each of these f of negative x. So I just replace all the x's with negative x. Make sure you put them in parentheses so that you can keep track of your signs. So in this first one, I substitute negative x in for the x values. And then a negative number to the fourth power gives us the same thing as a positive number to the fourth power, because negative x times negative x times negative x times negative x, there's 4 negatives. And so that means that they cancel each other out and we end up with a positive result. Minus, same thing happens here, negative x times negative x is the same thing as x squared. And then nothing happened to that constant. So f of negative x will end up equaling x to the fourth minus x squared plus 2, which is the same thing as f of x, which means that this function is even. On the next one, we have f of negative x equals negative x to the third minus negative x plus 3. So I end up getting negative x to the third, because a negative times a negative times a negative is negative. And then minus negative x is the same thing as plus x plus 3. If you think about our original function, so it does not match our original function, so we know it's not even, okay? But then if you think about what would the negation of this function be? If I were to negate this function, I should end up, because I'm just distributing the negative, I should end up with negative x to the third plus x, which looks familiar, but then it should be a minus 3. So this is not odd either. So this is an example where it's neither even or odd. Okay. On this last one, we have f of x equals x to the third minus x. So when we find f of negative x, we end up with negative x to the third minus negative x. That gives us negative x to the third plus x. And you think about our original function, if we negated that one, we would end up with exactly what I just found, which is equal to negative f of x. So therefore, this one is odd. The next thing we're going to look at is piecewise functions. In order to make sure that we're ready for analyzing piecewise functions, we need to make sure that we know our inequality signs. So if you don't know these, go ahead and pause and write them down. The big thing to know, though, is that these first two symbols, you end up with an open circle on the graph. These two symbols, you have a closed circle on the graph. And that's something similar to what we saw in our first objective, where we were graphing inequalities on a number line. And so it's the same idea. Okay, so if I include the number with the or equal to, then we have a closed circle. If it does not have the or equal to, then it's not, that number itself is not included, and so we have an open circle. So we'll see that in the graph, and then we have to translate it for our function, or for evaluating like our domain and range in our function, or determining other information about our function. So we're going to look at graphs of piecewise functions. Piecewise just means it's multiple functions broken into pieces over certain intervals of the domain. So you'll always see for piecewise functions these curly brackets, and it defines the function in different ways depending on what your x values are. So for this first one, we have the function f of x is equal to x squared plus 1 when x is greater than 0. And then we have it equal to x minus 1 when x is greater than or equal to 0. And then they've graphed it for us already. So you can see that from negative infinity to 0, it's a parabola. And from 0 to infinity, it is a line. And that makes sense because the x squared plus 1 is a quadratic and the x minus 1 is a linear function. What we're doing here is we're actually evaluating for values of x and determining what the value of the function is at these different values of x. So the first one is f of negative 1. So I come to negative 1 and look on my graph of my function. F of negative 1 is equal to 2. That's where I put the point on the graph in red. I can then evaluate f of 5. So I go to 5 on my x-axis and then go to where the graph is. Where x equals 5, the function equals 4. Now I go to where x is equal to 0, which is here. And then notice it's split into 2. That's the point at which it becomes piecewise because it's broken into 2 pieces. So what I have to do is I have to look at the part of the function that's actually filled with a solid dot. So when x is equal to 0, f of 0, or the function, is equal to negative 1. Okay, so that's just going back and being able to evaluate different values of the function at different x's based on the graph. Here we go. So in the first example that we had, the graph was provided for us, so we used the graph to find the values. On number 6, we do not have the graph, and so what we have to do is we have to substitute in the value depending on where the x value lives. I'm using air quotes around lives, based on the ranges of the domain or the intervals on the domain. So essentially, like here we're told the function h of x is equal to x squared plus 3 when x is less than 2. So anywhere where I'm evaluating x is less than 2, I'm going to evaluate it with this function right here. Anytime for the next portion, the h of x is equal to 7 if x is between 2 and 4 inclusive, because the signs are less than or equal to. So it essentially says h of x is equal to 7 for x's that are greater than or equal to 2 or less than or equal to 4. So anything that lies between 2 and 4, including 2 and 4, we evaluate with what I've circled in purple. And then lastly, our function is h of x is equal to 2x minus 1 when x is greater than 4. So any x values that's greater than 4, we evaluate with this part of that piecewise function. So the way we do this, though, is that we take the value and substitute it into the corresponding part of the function. So for h of 1, we're actually doing 1 squared plus 3. 1 squared is 1. 1 plus 3 is 4. Okay, and we practiced with evaluating functions before, so this shouldn't be new. This is definitely in our first week 2 objective. It's some of those prereq topics. For the second one, h of 3, when x is equal to 3, h of x is equal to 7. Same thing for this one. When x is equal to 4, it's still within this part of the domain, and so our function just evaluates with the number 7. And then for the last one, h of 5, when x is greater than 4, so 5 is greater than 4, we evaluate it by doing 2 times 5 minus 1. So that's our h of 5. And so we get 10 minus 1, which is 9. So we can evaluate a piecewise function from a graph. We can also evaluate it from its equations based on where our x values lie in these inequalities that are defined and defining the function. Now we're going to graph a function. So this function, f of x, is equal to 1/2 x plus 1 when x is less than 2. It's equal to negative x minus 1 when x is greater than or equal to 2. So here's what we need to do. We can make an xy table if we want, or f of x table to find values, or if you know the shorter way of graphing a linear function, you can use that as well. I'm going to do the shorter way for this first part because the y-intercept would be included on this graph. Okay, so essentially, when I graph a y equals mx plus b linear function, I first graph the y-intercept, which in this case is positive 1. And then the 1/2 there is my slope, which tells me the rise over run. So I go up 1 over 2. So I end up right there. But it's not evaluated at 2 for this part, so that's going to be an open circle. Let me draw that a little bit better. Okay, and so again, we can follow and make more lines. We can go down 1, left 2, down 1, left 2, and then we have this part of our function. For the second part of our piecewise function, our graph is negative x minus 1 for x's that are greater than or equal to 2. So what I can actually do there is I could graph it the same way and graph the the y-intercept, but know that I'm going to have to erase the part that's less than 2. So I'll show you what I mean by that. My slope is -1, so that means I go down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1. But this function, which typically would look like this in both directions, only starts at 2, where x equals 2. So that is the second piece of my function. Now, if I wasn't sure about that, what I could do is I could have checked values for -1. Actually, because it's 1/2, I might pick and be selective and say, check x value for -2, 0, and then check the value at 2 for the red part, just so I can get my open circle. So for these 3 values, I would use the 1/2 x plus 1. Then I would check for 2 for my closed circle, and maybe 3 and 4 to get additional points. And just know that for these, I would be evaluating this with -x minus 1. Okay, and I can make a table, and then I can draw both parts of those graphs. Okay, so there's kind of 2 ways that you can do that in a nutshell. All right, I'm going to go ahead and pause this so that it's not getting too long. There will be a part 2 in this video where we'll look at increasing and decreasing intervals and maxima and minima. So please make sure you watch part 2. Thank you.